All right, so part 5, sets and operations on sets, and there will be 3 questions from this section. Okay, so here we have A is 146, B 2346, C is 256, and then we have the universal set is all numbers from 1 to 7, and we just have a bunch of different things that we need to find here. So let's just go ahead and do these. Okay, so part 1 is A minus C intersected with B complement. So I'm just going to substitute in the different parts here, and then I'll work on them. So I'm substituting in A and C and B complement. Okay, and so I'm going to work on the part in the parentheses first. So the set 146 minus 256. So you take everything in 146 and then you delete anything that was in 256. So basically I'm only going to be deleting the 6. Okay, so this is going to be 1, 4. So I delete the 6. So that deletes. And then I'm going to have this intersection here, and now let me go ahead and do the complement. So the complement of the set containing 2, 3, 4, 6 is going to be everything that's in the universe and not in 2, 3, 4, 6. So basically everything in 1, 2, 3, 4, 5, 6, 7 that is not 2, 3, 4, or 6. And so this is going to leave me with, I'm going to have 1, I'm going to have 5, and I'm going to have 7. Okay, so now that I'm down to this point, I'm just doing an intersection of the set 1, 4 with the set 1, 5, 7. So that is everything that's in the overlap. Remember, when you have the intersection of 2 roads, that's where they overlap at. So the intersection is the overlap. So this is just going to be 1. Okay, number 2. So I'm doing A, which is 1, 4, 6, crossed with, so Cartesian product with the complement of B, which I just found the complement of B, so this is not too bad. Okay, so let me go ahead and do the complement, and then I will do the Cartesian product. So the complement of B, everything that is not in B, but is in the universal set. Again, that's just 1, 5, 7. Okay, so now what I have to do is I have to list all of the ordered pairs, where the first thing in the ordered pair comes from the first set, and the second thing in the ordered pair comes from the second set. So you just want to be really systematic when you do this. So first I'm going to do all the ones that start with 1, and there's going to be 3 of those. Okay, and those are going to be, so I'm going to use the sets in the second set there, which is 1, 5, 7. So this is going to be 1, 5, 7. Okay, then I'm going to do all the ones that start with 4, so that'll be 4 and 1, and then 4 and 5, and then 4 and 7. And then all the ones that start with 6, so this is going to be 6 and 1, 6 and 5, and 6 and 7. And that's it. So if you have 3 things in the first set and 3 things in the second set, you're going to have 9 things in your Cartesian product. Okay, part 3. So B complement again, which I know how to do, and then C union A. Okay, so let me write out, let me just substitute in all the different little pieces and parts for A, B, and C. And then I will perform the operations. So C is going to be 2, 5, 6, and then union with A, which is 1, 4, 6. Okay, so I know how to do B complement. That is just 1, 5, 7. So things that are not in B but are in the universal set. And now I have an intersection, and now let me simplify the part that was in the parentheses. So C union with A, that's everything that's in C or in A. So you basically just smoosh C and A's sets together into one big set. So you want to think of union as being like marriage. C and A are getting married, they're going to share all their stuff. So everything that's in either C or in A. So let's see, I'm going to keep everything from C, so I'll just write all the stuff from C down first. And then I'm going to add in anything from A that I didn't already write down. So I'm going to get a 1, and I'm going to get, let's see, a 4, and then I already had the 6. Oops, this is a typo here. Okay, so now I'm just doing the intersection of these two sets. So everything that's in the overlap of these two sets that are remaining here. So what is in both of them? They both have a 1. They both have a 5. They don't both have a 7. They don't both have a 6. And they don't both have a 4. So I believe that's it. So just 1 and 5. Okay, so number 4. So the union of A with B complement again. I guess I did a lot of B complements, didn't I? Okay, so A is 1, 4, 6. And then B complement, so that's going to be 2, 3, 4, 6 complement. So I'll do B's complement first. Okay, so the complement of B is again just 1, 5, 7. Sorry, that really doesn't look like a curly brace. Okay, that's a little better. All right, so now the union of these two things, so we're just going to smoosh them together, everything that was in the first one or in the second one. So I'm just going to write the first one again, 1, 4, 6, and then I'll add in anything that was in the second that I didn't already put. So that's going to be 5 and 7, and then I already had the 1. Okay, that's it. I'll go to the next slide for the rest. Okay, so number 5. So A cross C minus B. Okay, so I'll just fill in all the little pieces and parts again. Cross, and then C is 2, 5, 6, and then minus, and B is 2, 3, 4, 6. Okay, so I'm going to do the part in parentheses first, the minus. So 1, 4, 6 will stay the same, and Cartesian product. Okay, so the minus, so I'm going to take everything in 2, 5, 6, and I'm going to take away anything that was in 2, 3, 4, 6. Okay, so the 2 is going to be taken away, the 5 is going to stay, and the 6 is going to be taken away. So that's going to leave me only the 5. Okay, so that makes this Cartesian product pretty easy. So this is the set of all ordered pairs where the first thing is in the first set and the second thing is in the second set. So they all have to end with 5, and then they can either start with 1, 4, or 6. Okay, so I just get those 3 ordered pairs. All right, number 6, so I'm doing the power set. I put it in parentheses that it was the power set because I couldn't quite make the same script P that was in the textbook. So this is the power set of A minus C. So let me do the A minus C part first. So that's going to be 1, 4, 6 minus 2, 5, 6. So I'm going to take away anything in 1, 4, 6 that was in 2, 5, 6. So I'm going to take away the 6. So this is going to be the power set of just 1 and 4. So just to remind you, the power set, that is the set of all possible subsets of the set. Okay, and you want to list them off systematically, starting with the smallest. So the smallest possible subset of the set containing 1, 4 is the empty set. And then we can have sets with just 1 element each. So there's 1, and there's 4. And then we can have the set with 2 elements, which is the whole thing, 1, 4. And once you've gotten up to the largest possible set, which is the original set, then you're done. So that's all the possible subsets of the set containing 1, 4. Okay, number 7, A minus C intersected with B. So we just did A minus C, so that part's not too bad. So this is 1, 4, 6 minus 2, 5, 6. And then intersected with B, which is 2, 3, 4, 6. Okay, so I'll do the parentheses part first. So I'm taking away anything, so I'm starting with 1, 4, 6, and I'm taking away anything from 2, 5, 6. So that's going to get rid of the 6. So I'm just going to have 1, 4. And then I'm intersecting that with 2, 3, 4, 6. So remember the intersection, that is the overlap. So anything that's in both of those sets, and I think it's just 4. Okay, number 8. So we're doing the power set of B complement. So B complement is going to be 2, 3, 4, 6 complement. Oops. Okay, so the complement of that, oops, I'm doing typos all over the place. Okay, so the power set of, so the complement of B is everything in the universal set that is not in B. So that's 1, 5, and 7. Okay, so now I'm doing the power set of 1, 5, 7, so that is the set of all subsets. So the smallest subset would be the empty set, and then we can have the next smallest would be each element by itself. And then the next smallest would be 2 elements at a time. So we could have 1, 5, or we could have 1, 7, or we could have 5, 7. And then finally, the largest subset we could have would be the entire original set, which is 1, 5, 7. These curly braces are really devolving. Okay, and that's it. All right, number 9. So number 9, A complement union C minus B. So I'll just fill in all my little pieces and parts. This is 1, 4, 6. Complement union with C is 2, 5, 6 minus B is 2, 3, 4, 6. Okay, so first I'm going to do the part in parentheses, and I can also do the complement now. So the complement of A is everything that's in the universal set that is not in A. So the universal set is 1, 2, 3, 4, 5, 6, 7, and the ones of those that are not in 1, 4, 6 is 2, 3, 5, and 7. So that is A complement. And then I'll do the parentheses part. So I'm going to take everything in 2, 5, 6, and I'm going to take away everything that was in 2, 3, 4, 6. So I'm going to take away the 2, I'm going to take away the 6. So that's just going to leave me with 5. And I don't really need these parentheses here. Okay, so now I'm doing the union of 2, 3, 5, 7 with 5. And so I'm just going to smoosh those two together, but 5 is already in the first one. So this is just going to be 2, 3, 5, 7. Okay. And finally, I'm going to squish number 10 at the bottom here. So number 10, C minus B union with A. So let me just fill in all these parts here. So this is 2, 5, 6 minus 2, 3, 4, 6. And then union with A, 1, 4, 6. Okay, so let me do the part in the parentheses. So I'm starting with 2, 5, 6, and I'm taking away 2, 3, 4, 6. So that's going to take away my 2 and my 6, and that's just going to leave me with the 5. Okay, and then I'm unioning that with 1, 4, 6. So I'm just, this is just the set containing anything that was in 5 or in 1, 4, 6. So that's going to be 5, 1, 4, 6. Okay, that's it. Okay, so for 11 through 14, you have to either draw a Venn diagram or make up explicit examples of sets A, B, and C that have the following properties. So let us do number 11. So for number 11, I'll just do both types, just to show you what they both would look like. So for the Venn diagram, I would need B to be inside of A. So let me draw that. So here's B, and it's inside of A because it's a subset of A. Okay, then I also need B and C's intersection to not be empty. So B does need to intersect with C, at least somewhat. And then I need C minus A to be empty. So in other words, if I start with C and I take away everything that's in A, that would leave me the empty set. So this part right here, that last part, that is actually like a very subtle way of saying that C is a subset of A. Since the only way, if you start with C and take away everything in A, the only way you end up with nothing is if C was already contained inside of A. So those two things are like an equivalent statement. So C does need to be a subset of A, and B and C's intersection should not be empty. So I'm just going to draw C like this. Okay, so that's C. And then if we wanted to do explicit examples, then we could do it like this. So I could have A, B, and C, Okay, so B and C need to be subsets of A, and they need to overlap at least a little bit. So why don't I make B like that, and then C could be like that, and then A could be, so A needs to contain both of them, so like that. So with this, you just want to check again, is B a subset of A? Yes. Is the intersection of B and C non-empty? It would be 2, so that's not empty. And then is C minus A, if I start with C and take away everything from A, is that empty? Yes, because I would take away both the 2 and the 3. Okay, so let's go over number 12. So in this one, the first thing is telling us that A and C's intersection should be empty. So what that means is we can draw A and C, and they should not overlap at all. Okay? And then as far as set B, so the important things about B are that B minus C should be B. So that means that if we take away all the elements in C from B, it doesn't do anything. So in other words, B should be outside of C as well. So B is not going to overlap with C at all either. So this is like equivalent to also saying that B and C's intersection is empty. Okay? And then finally, A intersected with B should be not empty. So we need that B and C's intersection is empty and A and B's intersection is not empty. So you can just do it like this. So make B over here like this. And so another example you could do for if you want to do explicit sets, let's see. So A and C's intersection is empty. So maybe I'll just have A be like 1, 2, and then C could be, I don't know, 3, 4. So their intersection is nothing. And then B does not overlap with C, but it does overlap with A. So I can just do maybe 1, 5, like that. Okay, and then you can check all 3 of those conditions and make sure they're true. Okay, so number 13. All right, so A and B's intersection should be non-empty, and A should not be a subset of B. So if I just draw A and B like this, I think that'll be fine. So A is not a subset of B, but their intersection is not empty. And then finally, so this part is a little bit weird, so C minus A should actually equal B. So this part is actually a typo. This would be impossible to draw any sets like this. So what I meant to put here was C. So this is a typo. So C minus A should be C. In other words, if you take away A from C, that doesn't change C at all. So I'm just going to draw C out here like this. That'll work just fine. So then taking away anything in A from C does not affect C. And then so if we wanted to do explicit examples here, let's see, we could do, so A and B should not have an empty intersection, but they should not be such that A is a subset of B. So I could do like this, for example, 2, 3. And then for C, I can just make C something completely different, like that. Okay, so for 14, so 14B needs to be a subset of C. So C is going to be here, and then B is going to be inside of it. And then A unioned with B should equal A. So this is a little bit tricky, but basically this is saying if you smoosh A and B together, you don't get anything more than you had with just A. So this is like another way of saying that that B is a subset of A. That's the only way that would happen. So B is also a subset of A. And then finally we have that A and C's intersection should be completely empty. So this is quite a challenging problem actually, because if you think about how you're going to draw B as also being a subset of A, well, B is inside of C, so then if B is a subset of A, how could A and C's intersection be empty? So this one will only work under the following condition if B is the empty set. Okay, so if B is the empty set, then B will be a subset of A, since the empty set is a subset of any set, and it will also be a subset of C. And then we just have to draw A and C in such a way that they are completely separate from each other. They have an empty intersection. So like this. And then B is just the empty set. So it has nothing inside of it. Maybe I shouldn't even draw that dot, in fact. I'll just erase that. Okay, and then if we wanted to do explicit examples, we just have to make A and C completely separate. And then B is the empty set. Okay, so part 6, the element method of proof. So there will be one question similar to this on the real test. Okay, so for this problem, we have to do the element method of proof, and I'm going to remind you of what that is if you don't remember. It's also in those places in the textbook that I mentioned. So we're going to prove that for all sets A, B, and C, if A is a subset of B, then A union C is a subset of B union C. Okay, so for our proof, so the first thing we have in our statement here is a for all, so we're going to translate that to a let. So we're going to let A, B, and C be sets. Okay, and then we have an if-then statement. So we're going to use the direct method of proof, which means we assume the if part, and then we show the then part. So we're going to assume A is a subset of B. Okay, and then we will show the following. A union C is a subset of B union C. Okay, so in order to show that one set is a subset of another set, this is where you use the element method of proof. So we assume, or let, X be an element of A union C. That should be a capital C. And then we will show that X is also an element of B union C. So that's what's called the element method of proof, because it's all about elements. Okay, so what do we get from this assumption? Since X is an element of A union C, that means, okay, what does that tell us? So that tells us that either X is in A or X is in C, or it could be both, but that's covered by the or statement. Or is always inclusive. It includes the possibility of both. Okay, so now what I'm going to do is, because we got an or statement, this means we have two cases. So there are two cases, and those are coming from the or statement. So case 1 is X is an element of A, and then case 2 is X is an element of C. So one of these has to be the case. So as long as we can show that both of them lead to X being an element of B union C, then we will have shown it in every case. Okay, so first of all, if X is an element of A, what does that tell us? Okay, well, since A is a subset of B, that would tell us that X is also an element of B. That's what it means to be a subset. That means everything that's in A will be also in B. Okay, so if X is in B, then X is in B union C, since B union C includes everything that's in B. Okay, so that case is finished. We showed that X was an element of B union C. So now let's look at the second case. So if X is an element of C, then we just directly have that X is an element of B union C, because that includes B union C includes everything that's in B. Or sorry, in C. Okay, so in either case, we get that X is an element of B union C. Therefore, and this is optional, you don't have to include this therefore, but what this is showing you is that A union C is a subset of B union C, and we're done. Okay, so for number 2, for all sets A and B, if B is a subset of A complement, then A intersect B is empty. Okay, so this one is still the element method of proof, but it's a little bit of a different approach. So let me show you how to do it. So we have the for all, so we're going to translate that to a let. So let A, comma B be sets. Oops, it's not how you spell sets. Be sets. Okay, and then we have an if-then statement, so we're going to assume the if part. Assume B is a subset of A complement, and then now we need to show the then part. So we will show this, which is the then. Oops, that is not an equal sign. Okay, so how do we show that a set is the empty set? So what we're going to do is we're going to use the method of proof by contradiction. So let me just make a note of that. By proof by contradiction. So in other words, we're going to assume that A intersect B is not empty, and then we'll show that leads to a contradiction. So suppose that there is some element in this intersection of A and B, so that would mean that it was not empty. So suppose there is an element in there. Okay, now we need to show this leads to a contradiction. So what does it mean for X to be in the intersection of A and B? That means that X is an element of A and X is also an element of B. Well, what else can we use? So what is the other information that we have here that we haven't used yet? Well, we haven't used this subset thing that we assumed, so let's use that. So since X is an element of B and B is a subset of A complement, that means that X is also an element of A complement. Okay, that's what it means for B to be a subset of A complement. All the things in B are also in A complement. Okay, so now we have a contradiction. So this is a contradiction. We cannot have both X is an element of A and X is an element of A complement, because A and A complement are disjoint. Okay, so that means our supposition was wrong. So there is no X in A intersect B, so A intersect B is empty. And that's it. Okay, number 3. So we're just going to do this the same way as number 1. So we start with translating this for all statement into a let statement. So let A, B, be sets. And now we have an if-then statement, so we're going to assume the if part. So assume A is a subset of B. And now we're going to show the then part. So we will show B complement is a subset of A complement. Okay, so how do we show that one set is a subset of another set? So you assume or let or suppose that X is an element of the first one. So X is an element of B complement. Okay, and now we need to show, so we will show X is an element of A complement. Okay, how are we going to do this? Well, since X is an element of B complement, what does that mean? So since X is in B complement, that means that X is not in B. That's what that means. So let's think about this for a second. So what else do we know? The only other thing we know is that that A is a subset of B. So think about this very carefully. So if A is a subset of B, you've got B like this and A like this. And where is X? X is not in B. So X is like over here, not in B. So where is it also not? It's also not in A. So we're just going to say that. So since A is a subset of B and X is not in B, we also know X is not in A. Since if X were in A, it would not, then X would also be in B, but X is not in B. Okay? I hope that makes sense to you guys. So since X is not in A, that means X is in A complement. So that's it. Okay, let's look at number 4. So for all sets A, B, and C, if C is a subset of B minus A, then A intersect C is empty. Okay, so we'll just start off this proof like all the others. we'll translate this for all statement into a let statement. So let A, B, C be sets. Okay, and now we have an if-then statement, so we're going to assume the if part and show the then part. So assume C is a subset of B minus A. Okay, then we will show the then part, A intersect C equals the empty set. Okay, so how do we show that something is empty? All right, we're going to do it by contradiction. So let me just make a note of that. By contradiction. Okay, so for our contradiction, we're going to suppose the opposite of what we want to show. So we suppose that the intersection is not empty, which would mean there is some element in the intersection, and we'll show this leads to a contradiction. So suppose X is an element of A intersect C. Okay, so what do we know about X from this statement here? Well, it's in an intersection, so that means it's in both of those sets. So it's in A and it's in C. Okay, now at this point, what else can we say? So we've used everything except for this subset assumption that we made. So let's use that. So since C is a subset of B minus A and X is an element of C, that means that X is also an element of B minus A. Okay, so this is quite helpful actually, because that means, so since X is an element of B minus A, what does that tell us? That tells us two things, that X is an element of B and X is not an element of A. So that's very helpful because that's our contradiction right there. So this is a contradiction. We can't have both. We can't have both X is an element of A and X is not an element of A. Okay, so that means our supposition was wrong. So there is no X in A intersect C. That was our supposition. So there is no X like that. Oops. There is... Oops. I'm sorry, guys. Okay, so there is no X in A intersect C. So A intersect C is empty. And that's it. Okay, number 5. So we'll start off our proof the same way. We're going to let A, B, and C be sets. And now we have an if-then statement, so we're going to assume the if part. So assume A is a subset of B, and B is a subset of C. Okay. And then we will show the then part. So we will show that A is a subset of B intersect C. Okay, so how do we show something is a subset of something else? So we're going to assume or let or suppose that X is an element of the first set, A, and then we will show that X is also an element of the second set, so B intersect C. Okay, let's go ahead and try this. So let's see, what do we know? So far, all we know is that X is an element of A, so we're going to have to use that. So X is an element of A, and then we're going to have to use our other assumptions, so that A is a subset of B and that B is a subset of C. So let's use the first one. So since X is an element of A and A is a subset of B, that means that X is also an element of B. Okay, that's pretty good because now we're getting closer to being able to show that X is an element of B intersect C, because we've got half of it. All right, now how are we going to show that X is also an element of C? Well, we do also know that B is a subset of C. So since B is a subset of C and X is an element of B, that means that x is also an element of C. Okay, so we have both things that we need. So since B is an element, still trying to master this pen, guys. So since x is an element of B and x is an element of C, that means x is an element of B intersect C. And that's what we were trying to show. So we're done.